In this video, I'm going to attempt to explain the difference between electromotive force and potential difference in the context of Faraday's law and Module 6, electromagnetism in HC physics. So let's consider a very simple setup. You've got a bar magnet with two poles, north-south. You've got a coil of wire that's just big enough for the bar magnet to fit through. And this coil of wire is connected to an ammeter. So a bar magnet you've got here. You've got a coil of wire. Okay, let's say there's 3, 4, 5, 6 loops or 6 turns, same thing. So basically get a wire and you just wind it up into loops or turns. And this here is an ammeter. This measures current. So from everyday experience, we know that if you have a coil of wire, or just a wire for that matter, and you hook it up to an ammeter, there should be no current reading on the ammeter. Okay, there should be no current, because current by definition, from year 11 physics, so this means by definition, right, equal sign and a dot on top. I should say, by definition, current is the amount of charge flowing through a certain amount of time. Flowing through a point in a certain amount of time. So it's basically, typically in a circuit, the flow of positive charge. That's what current is. So there's no current when you connect a wire, loop of wire, to a ammeter, because there's no energy provided, right, for the current to move, the charges to move. So what Faraday found was that so this was in the 1800s, if you get a magnet, bar magnet, let's say, and you move it in and out of the coil at some speed, so what's happening is there's a magnetic field. So magnetic field lines, they start at the north and end at the south. The coil experiences a changing magnetic flux. Okay, so there's a magnetic field, but let's call it B for the bar magnet. But let's say you're standing where the coil is, when there's magnetic field lines coming in and out of the coil, you're having a changing magnetic flux. Okay, that's what the delta here means. In physics, in maths, it means changing magnetic field, which is basically, so a changing magnetic field over time. This translates to a change in magnetic flux, because when you have a changing magnetic field through a certain amount of area, through the coil, you've got, by definition, a magnetic flux. And that's a symbol, Greek symbol phi. Okay, the delta is changing. So a change in magnetic flux is experienced by the coil. And according to Faraday's law, this induces an EMF, an electromotive force, given by a curly E. This is called epsilon, Greek letter epsilon. So Faraday's law of electromagnetic induction, I should say, of EM induction, is given as follows. Epsilon is minus n delta phi over delta t, where epsilon is the electromotive force. I'll talk about that now. Electromotive force, it's got units of volts. N is the number of turns. Okay, in this case there's 6. And delta phi, that's the change in magnetic flux over time. So magnetic flux, the change in magnetic flux has units of Tesla meter squared. Okay, so the amount of magnetic field lines going through an area, m squared. And when you have motion, there has to be relative motion between the magnet and coil, you can only get an electromotive force then. I'm going to talk about this now. There's a bit of confusion with students when it comes to electromotive force and potential difference. Potential difference is what you explore in junior science, typically year 9 science. But EMF is basically, so electromotive force, EMF for short, is basically the voltage induced in the coil, okay, due to the changing magnetic flux, according to Faraday's law. But potential difference, PD for short, this is usually measured between 2 points. So let's suppose 2 points, the two ends of that coil, if you unwind it, two ends of the coil, if you were to measure the voltage, between these 2 points. This is called the potential difference. When there's current actually flowing, I should say. So the electromotive force, think of it as like a hand. I like to think of it as a hand. This will push the charges in the wire along a certain direction. Let's say the electrons. And when the charges are moving, you've got current and the ammeter picks up a current reading. So this can only happen when there's a changing magnetic flux, when there's a magnet moving in and out of the coil. This induces an electromotive force like a hand, and this pushes these dots, electrons along the wire, and that gets picked up by the ammeter. And you can measure the potential difference in this circuit here, in this closed circuit, only when there's current flow. If there's no current flow, if there's no magnet, you can't measure potential difference. So potential difference is basically a consequence of electromotive force in this case. So electromotive force, EMF, this results in a potential difference. And that's what the difference is between electromotive force and potential difference. This here is the voltage induced in the coil. And potential difference is the consequence of the electromotive force when there's current actually flowing. And it's the difference in potential between 2 points, potential energy. Both have got units of voltage, but one causes the other. And how does Lenz's law come in? Well, as I mentioned, changing magnetic flux, delta phi over delta t, induces an EMF, according to Faraday. Right, and the faster the magnetic field changes, the greater the EMF, the greater the voltage. Lenz's law states, this is what the minus sign is, Faraday's law, the minus sign is literally Lenz's law, states that the direction, so the EMF induces a current in the coil of wire. Lenz's law states that the direction of this induced current will oppose the change that's causing it, will oppose the change in magnetic flux, because changing current induces a magnetic field of its own, by definition. And these two magnetic fields interact. And the induced current induces a magnetic field, and that magnetic field opposes the original change that it caused, that caused it in the first place. So to summarize, Faraday's law states that you need a changing magnetic flux in a coil to induce an electromotive force, like a pushing force. That creates a voltage. Voltage by definition is like a pushing force, and that pushes charges in a wire, and that creates a potential difference.